our model molecule. This purple thing here is the central atom. The most common examples used as central atoms are carbon or oxygen atoms. These white spheres are bonding atoms, usually hydrogens. For our example, let's just pretend that the purple atom is oxygen and the white atoms are hydrogen, creating H2O, or better known as water.
Within this water molecule, we have two different classifications of this three-dimensional structure. The molecular geometry refers to the bonding orientation that the oxygen has with the water. In this case, on the bottom of the screen, it shows that the single molecule is bent. But the electron geometry posed by it again shows it as tetrahedral. It is important to understand the different configurations so as not to confuse them. While molecular bonds and lone pairs drive the momentum of the intermolecular forces, one other important aspect to take note of is the bond length, which can be measured in a form of units called angstroms. And the length in angstroms of each bond, or in many cases double or triple bonds, is dictated by the size of the atomic radii of the central atom, which can determine the, quote, freedom exhibited by the electrons. And for whoever's watching this, this is what we call a methane atom, which is basically a hydrocarbon, which is just one carbon connected to four hydrogens. And if you want to know anything further about them, these types of atoms are very boring. The only thing you can really do with them is burn them, which is why we use methane as a fuel source.
How do lone pairs affect bond angles in real molecules? The orbitals that lone pairs occupy are shorter and wider than the orbitals of bonding pairs. The lone pair's electron is not involved in any bonding, making it free, as it is only influenced by one nuclei. Here. Bonding pairs are more stabilized because they are attracted to two nuclei. Here. Because of these factors, lone pairs occupy more space. This big electron cloud then repels bonding pairs with greater force than what bonding pairs repel each other with. This pushes bond pairs closer together, away from the lone pairs. This is how we end up with different bond angles. Today we learned how the relationship between electron pairs and bonding atoms affects the bond angles in a molecule, showing us how we end up with different geometries, and how atomic size affects the bond lengths of molecules. So why is this all important in the grand scheme, you might ask? By understanding molecular geometries and electron distribution, chemists working in pharmaceutical companies can use these general premises to create drugs that can help people live healthier lives.